Here's a problem which you might get as a high school student doing something like IB or A levels or equivalent, um, that you might see in your electromagnetism chapter in physics. And this question requires us to look at an infinitely long and straight wire. And what we have to do is we have to find the magnetic field at a certain point P, which is stationary, and it's also at a distance, at a fixed distance x away from the wire. So to do this, we are going to first have to use the Biot-Savart law, which I'm not going to talk in detail. There are plenty of resources out there that can help you understand it better, but I'm just going to write the differential form of it. So let me write the name here. So we're looking at the Biot-Savart law. So what this says is that for any wire with current in it, each each section of the wire, each infinitely small element, is responsible for creating a small component of magnetic field at this point P. So let's say that I have a coordinate system which has an origin O here. So this is my X and this is my Y. And then this piece of wire will have a length dy. So the Biot-Savart law says that this piece of wire, which by the way has current going through it, so let's say the direction of the current is upwards. So this piece of wire of length dy will affect the magnetic field at point P, and it will actually create a small amount of magnetic field at point P, which is going to be called dB. So P in this case would be the total amount of magnetic induction at point P, and the the quantity dB is just represents just the contribution of this infinitely small piece of wire which has a length dy. So the Biot-Savart law, what it says is that the contribution dB, which is a vector by the way, is equal to something we name mu 0 over 4 pi. So mu 0 is the permeability of the medium, and then we've got a cross product between dl and r. So dl, or I should say in this case, I'm not using L, but I'm using Y. So dy is a vector which has the magnitude of this piece of wire, and it has a direction, it has the same direction as the current. So in this case, it would be a vector with length dy and pointing upwards. And r is the distance from this piece of uh, wire to my point P. So it would be this vector. So we have the cross product, and this is divided by the distance from, let's call this point A, divided by the distance from A to P, which is R cubed. So that's what we are going to use, and this is what will tell us what the overall effect is after we do some integration. So the first thing I would do is try to figure out what this cross product is equal to. So we have dy cross product with r equals, so we're going to use the usual formula, which is the determinant of ijk, and then we have to put in the first row the components of dy, right? So dy is pointing upwards, so it has a j component only, and the length is just dy. And then it has no z component. So the z component would be this way, like towards us, out of the screen. And then r is this vector in pink, whose components are x, And remember, x is constant. This is going to be useful later. So x is a constant. And the j component is actually going to be minus y, because the distance from the origin to my element, to my wire element, is going to be y. Its length is dy, and r is this vector that points downwards from A to point P, right? So it has a j component, which is negative um, y, because it points downwards, and then it has nothing in z. So if we try to solve this determinant, you can see that it only has a k component, and then this would be minus x dy, and that's it. So we can sub this in here, and that will tell us that dB will be equal to mu 0 over 4 pi, and then we have a minus from here, and we have x dy over r cubed times k. So this says that the magnetic field due to that piece of wire will be in the negative z direction. So in other words, that magnetic field at dB here, which choose the same color, is pointing into the screen, right? Whereas my positive z direction, as you can see, it's out of the screen. So the only thing left to do at this point is to try to figure out what the overall effect is of the entire wire at point P. So if this is the contribution of, this piece of wire, what does the whole wire do? And to do that, we'll have to do an integration, of course. But the issue with that is that at the moment we have two variables. So we have this y, which changes as we move along the wire. So if we choose a different element, let's say here, then my y is going to be different. But not just the y, the r is also going to be different, because r is this vector, right? So ideally, we just want to express everything either in terms of r or just in terms of y. And spoilers, expressing it in terms of y is easier. So let's see how we do this. This triangle is a right triangle, which means that we can write r as the square root of x squared plus y squared, where only y is my variable, so x is constant. So if I do this here, let's say I'm just going to look at the value of dB. I'm going to ignore any direction for now. So this is mu 0 over 4 pi, and then x dy over. So r cubed will be basically this cubed, which is x squared plus y squared, and then this is to the power 3 over 2. Which is nice, because now we only have one variable, which is y. So to find the overall effect of the magnetic field, so to find B, we would have to integrate dB. So we integrate mu 0 over 4 pi x dy over, and this is x squared plus y squared to the power 3 over 2. And I will take out all the constants, which are mu 0, and I realize I forgot to add the current. So there's a current here as well, like this. So I have mu 0 times the current times x, because remember x is also constant, over 4 pi. And then we have the integral of dy over, I'm going to put the variable first, y squared plus x squared to the power 3 over 2. Now, I would also add the integration limits. And remember, we're integrating with respect to y, and this is our origin, which means that y starts from all the way down here, but this is an infinitely long wire. So this would start from minus infinity, and it will go all the way to plus infinity. And those are my limits. So my limits would be from minus infinity to plus infinity. And normally I have to, put an epsilon instead of infinity and write a limit in front of it, but I'm going to skip that part. So we have to solve this integral. which looks a bit messy. And one of the ways to do it is actually use substitution. So the substitution that I will use is y equals x multiplied by 10u. And you'll see why that makes things very easy. So the first thing I want to do is change the integration limit. So when y is minus infinity, I want to see what u is. So if I rearrange, 10u is also minus infinity, which means that u would be minus pi over 2. And then for plus infinity, we have a similar approach where u is pi over 2. So if we change the integration limits, or if we do this substitution, we have to change the integration limits from plus minus infinity to plus minus pi over 2. So that's the first thing. The next thing would be finding what dy is. So dy would be x, which is a constant again. And then when we differentiate this, this is just 1 over cosine squared of u times du. So that's done. And the last thing is figuring out what this becomes. So that is y squared. So y squared is just this squared, which is x squared tan squared of u plus x squared, and this is to the power 3 over 2. And if I factorize an x squared outside, I actually get an x cubed times tan squared u plus 1 to the power 3 over 2. So inside that bracket, if you use some trigonometric formulas, you'll end up with the fact that this will be 1 over cosine squared of u to the 3 over 2. And finally, this is x cubed over cosine cubed of u. So that's done. And now we can assemble everything and find what b is. So b is mu 0 over 4 pi times the current times x, and the integral is now from minus pi over 2 to pi over 2. So dy is x du over cosine squared of u, and then the denominator is x cubed over cosine cubed of u. So let's simplify some things. We have this x times this is x squared divided by x cubed is 1 over x. And then we can cancel this with the cube. So we'll just end up with mu 0 over 4 pi times I. And then this is also going to be divided by x. So let me write it here. And the integral just becomes from minus pi over 2 to pi over 2 of du divided by 1 over cosine, which is just cosine of u du. And that's a very simple integral, so that's just sine. We have mu 0 I over 4 pi x times sine of u from minus pi over 2 to pi over 2, and this is mu 0 I over 4 pi x. Sine of pi over 2 is 1, sine of minus pi over 2 is minus 1, so we get, this becomes 2. We can cancel out with this 4, and we get the final answer. I'll write it here. So we get b is mu 0 times I over 2 pi x. So this is the value of the magnetic field at the distance x away from an infinitely long wire. So what you can see is that this depends on, this constant, assuming that the current is constant, and it's inversely proportional to x. So if you want to plot it, so if you imagine my y-axis in this graph is the wire itself and x is the distance away from it, then the magnetic field actually tends to infinity as you approach the wire, and then as you move away from it, it will approach 0 asymptotically, right? So this would be my mu 0 I over 2 pi x. And that's the end of the question.